Okay, so I want to take a look at rational functions. A rational function is anything of the form f of x equals p of x over q of x, where those are both polynomials. We're going to focus on simpler examples as we do this, but these can actually get very complicated. In terms of simple examples, the simplest rational function, the most basic, is the reciprocal function, which has the parent y equals 1 over x. This is not something we've graphed before, but if you think about it, the big thing that we need to realize when we're doing math, we cannot divide by 0, right? And if I can't divide by 0, that would mean, of course, that x cannot equal 0. All right? So if I want to figure out how this graph looks, I'm going to pick some values for x and just take a look at what points I get, what the curve looks like. But I got to know that I can't have 0. So I'm going to go ahead and start. Just make a little chart here, x and y. If x is 1, then y is 1 over 1, which is simply 1. If x is 2, y is 1/2. If x is 3, y is 1/3. Okay? I can keep doing this. If I put in 4 for x, I'll get 1/4. 5 will get me 1/5, 1/6, 1/7, etc. And it looks like it's getting closer and closer to that axis. How about, though, I know I can't have x equaling 0. What if I looked at what happens between 0 and 1? What if I put in 1/2 for x? Well, then y would be 1 over 1/2. 1 divided by a fraction means I'm really multiplying by the reciprocal of that fraction, so I have 1 times 2 over 1, which is 2. Similarly, if I put in 1/3, 1 over 1/3 is 1 times 3 over 1, or 3. Okay? So those are positive values of x. What if I put in some negative values? If I put in, I'll go ahead and start with negative 1/2. 1 over negative 1/2 will be, well, it's basically the same problem over here. The difference is the negative sign, so I get negative 2. If I put in negative 1, 1 over negative 1 will be negative 1. If I put in negative 2, I'll have 1 over negative 2. Negative 3 will get me 1 over negative 3, and so on. So what do these points look like? Right here, negative 1/2, negative 2 is about here. 1, negative 1, negative 2, negative 1/2, negative 3, negative 1/3, and I get these points. So what is happening here? Well, here's the tricky part. I said that x cannot equal 0, which means what I have in the middle right here is a vertical asymptote. So I'm going to sketch the asymptote with a dashed curve. Now, additionally, as we thought more about this, if I put in 4, 5, 6, 7, 100 for x, I would have 1 over 100. Those values remain positive. On the other side over here, when I took 1 over a negative number, each time I got a negative number. So my curve is going to look something like this. I'm going to see that there are two separate disconnected branches, they're not connected, that squeeze in really close to these two asymptotes I see. The asymptotes in this case for this parent function are the two axes. Okay? But I can see I have two asymptotes. A vertical asymptote of x equals 0 and a horizontal asymptote of y equals 0. This is pretty typical for rational functions. They'll have both a vertical and horizontal asymptote. So in this case, with just 1 over x, I have two very simple asymptotes, x equals 0, y equals 0. Now, like any function in Algebra 2, we know that we can transform this. So let's look at the transformational form of the reciprocal function. Well, my transformational form is y equals a over x minus h plus k. These work the same way they have all year. A can reflect the graph. If it's negative, we can stretch or compress vertically. H translates left and right. K translates up and down. Now, if I am translating left and right or up and down, that's also going to move my asymptotes. My vertical asymptote then is x equals h. Comes from the 0 of the denominator. My horizontal asymptote is y equals k. Comes from this horizontal translation. No, I was right, vertical translation, sorry. Okay. All right, so what if I tried to graph something in the same family, but with translations? Let's take a look at an example like that. Here, I see f of x equals 3 over x plus 4 minus 1. I want to determine and sketch the asymptotes. That will be my first step. So for my asymptotes, I think about the denominator being 0. If x plus 4 equals 0, then x equals negative 4. That is my vertical asymptote. My horizontal asymptote, I look at all these numbers and I know that vertical translation is going to tell me my horizontal asymptote is y equals negative 1. Now mind you, these are lines, they have equations. Make sure that you are going ahead and writing equations. X equals negative 4 and y equals negative 1. Go ahead and plot those. X equals negative 4 is 1, 2, 3, 4 right here. Y equals negative 1 is down here. And I expect something like the first graph, where I get two separate branches squeezing in between these. They could be up here and up, they could be down here and up here. If there's a reflection, then instead I would see them in the opposite little quadrants right here. Now I said a few minutes ago, or I meant to, when you're graphing these, you're generally not going to have a lot of good points. So what you want to do typically is plot around 2 points on either side of the vertical asymptote. So I'm just going to think about what happens when x is, so if I'm on the right side of the vertical asymptote, I want to think about when x is negative 3 or negative 2 or negative 1. So if x is negative 3, I will have 3 over negative 3 plus 4 minus 1, which is 3 minus 1, or 2. If I were to put in negative 2, what would I get? I would have 3 over negative 2 plus 4 minus 1, which looks like negative 3 halves minus 1. Excuse me, positive 3 halves, because this is 2. 3 halves minus 1, which is 1 half. And I could keep doing this. If I put in negative 1, I would have 3 over negative 1 plus 4 minus 1, which is 3 over 3 minus 1, which is 0. So I can get more points, but the general idea that we want to have is this curve is going to get close to these asymptotes. So what is it going to look like apart from this? I'm going to see something that kind of shoots up through here, gets really close to the asymptote, comes down through here, gets really close to the asymptote on this side. What's going to happen down here? Well, I can pretty safely predict that I'll get a curve very similar to this, but down here. Let's go ahead and put in some points down there. If I put in negative 5 for x, I will have 3 over negative 5 plus 4 minus 1, which is 3 over negative 1 minus 1. Negative 3 minus 1, that's negative 4. Of course, I should also mention you can get these points on a calculator if you enter it in properly. You just have to be careful. And I could do the same thing if I put in negative 6. I will have 3 over negative 6 plus 4 minus 1, which is 3 over negative 2 minus 1. So that's negative 3 halves minus 1. So that's negative 1½ minus 1 right down here. Again, I know what the behavior is. These curves are going to pass through these points and then hug these asymptotes, get really close to them. So it looks something like this. So now, I've sketched the two branches of this function, and I want to think about the domain and the range. Well, for my domain, it looks like x takes on nearly every value, with one exception. It cannot actually reach this vertical asymptote. X is not negative 4. So commonly you might see something like all real numbers with x not equaling negative 4. In interval notation, I want to think about skipping over this. So x gets really small, negative infinity, and it's going to get very large, but before it does that, I keep going from negative infinity until I hit negative 4, which I have to skip over. Then I'm going to go from negative 4 to positive infinity. My range will be very similar. I see I have an asymptote. I know I had an asymptote of y equals -1. Y does not reach that value. So my range is all the real numbers except for -1. In interval notation, I can then write this as -infinity up to -1, but not quite including it, so I use parentheses. Then I go from -1 to infinity. So those are the domain and range of this function. So that's just a look at how you might sketch these things. One of the big things you really need to understand about rational functions is how to find those asymptotes. Okay? The points, you can always just plug in points, and if you do it carefully enough, you'll get good points. You can use a calculator in theory, and a calculator, of course, will do most of the work for you. Let's go ahead and take a closer look at how to find asymptotes. So again, general rational function has a domain of all real numbers except the zeros of the denominator. I know I can't divide by 0, so for example, in this particular problem right here, any values that make that denominator 0, I have to exclude from the domain. The zeros of the denominator may indicate a one-point hole in the graph. Those are more advanced functions of what we're generally going to deal with. So for us, we will see vertical asymptotes. So we need to get that in our head. The zeros of the denominator tell us about vertical asymptotes. So here I want to find the vertical asymptotes for each function. How am I going to do this? Well, I'm going to factor. X squared plus 3x minus 4. If I factor this, I know that x squared is x times x, -4 and 3. Well, if I do +4 and -1, I'll get that. So my vertical asymptotes are the two zeros of this. If I say x plus 4 equals 0, x minus 1 equals 0, then I get x equals -4, x equals 1. This function has two vertical asymptotes. How about the next example right here? X squared minus 1 over x minus 6 squared. So x minus 6 is the lone factor. It's squared, but it is still a single factor. So my vertical asymptote is simply going to be x equals 6. All right. Last one looks way more complicated, but again, when I'm determining the vertical asymptotes, I'm thinking about zeros of the denominator. Okay? So I want to factor this. X squared minus 7x plus 10, x squared is x times x. The factors of 10 that add to -7 are -5 and -2. If I set each of those to 0 and solved, I could see that my two asymptotes are x equals 5 and x equals 2. Know how to find these asymptotes. If you're ever asked to graph something, most of the time when you're dealing with one of these functions, you'll see something pretty simple like what we did on the front page. But if you're asked to find asymptotes, again, I can make these much more complicated. I can require you to factor and do all that fun stuff. So that's how you find a vertical asymptote for a general rational function. To find a horizontal asymptote, don't jump to any conclusions because it's somewhat different than what you might guess. To find the horizontal asymptote, what I'm going to do is compare the degrees or leading terms of the numerator and denominator. So, I have three possibilities. Either the degree of the numerator is less than that of the denominator, the degree of the numerator equals that of the denominator, or the degree of the numerator is greater. And I want to think about this. Right here, if I look at the leading terms, I see x over x squared, which simplifies to 1 over x. Now that's not an asymptote by any means, but what I need to think about as x approaches infinity, because I'm talking about end behavior when I talk about asymptotes, this is going to approach 0. So, in the case where the numerator has a degree less than the denominator, I will always have the same horizontal asymptote, y equals 0. How about in the case that the numerator equals the denominator? So again, if I compare the leading terms over here, I see 4x, I see 2x. 4x over 2x is equal to, well, the x's can be divided out, and 4 over 2 simply leaves me with 2. So in this case, I get 2 is my asymptote. Now, of course, it won't always be that way. What did we do here? I can say y is equal to a over b where these are the leading coefficients. Lastly, what about the situation where the numerator has a degree greater than the denominator? So 2x squared over x. Well, if I tried to simplify this, what I would get is 2x. Now here's the thing. Horizontal asymptotes deal with end behavior, so as x approaches infinity. Here, as x approaches infinity, I would get 0. As x approaches infinity here, it's going to get closer and closer to 2. As x approaches infinity here, it's not going to be bounded. This will tend towards infinity. Okay? As x approaches infinity, 2x also approaches infinity. Well, what does that tell me? In short, this tells me about the end behavior of this function, but for horizontal asymptote, there is none. So again, think carefully about this. When you're finding the horizontal asymptote of a function, you want to compare the degree and leading terms of the numerator and the denominator. Okay? Vertical asymptotes, you find the zeros of the denominator. Horizontal asymptotes, you're comparing the leading terms. All right, so let's take a look at some examples. You're asked to find the domain, vertical asymptotes, and any horizontal asymptote for these functions. So, domain comes from vertical asymptotes and what we call restricted values, the things that are not in the domain. So in this case right here, I know I want to think about for my vertical asymptote, where is the denominator equal to 0? And the answer is when x equals 6. When I'm thinking about my horizontal asymptote, I want to think about negative 4x over x. I can simplify that and get negative 4, which tells me my horizontal asymptote is y equals negative 4. Okay, so lastly, what about my domain? So the domain is everything but the restricted values or vertical asymptotes. So I need everything except 6. In interval notation, that means I'll go from negative infinity up, 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 but I got to skip 6. Next example. 2x minus 5 over x squared plus 9. If I go ahead and look at these, again, I want to think about the vertical asymptote first. X squared plus 9 equals 0. Well, that would mean that x squared is equal to negative 9, which has no real solution. This is only true for things with i's. So this has no real solution. Since there's no real solution, that means I will have no vertical asymptote, which will also in turn mean that the function has a domain of all real numbers. There are no zeros, there are no real zeros for this denominator, so my domain is all real numbers. How about my horizontal asymptote? Well, I'm going to compare 2x and x squared. 2x over x squared is 2 over x. And again, if I think about x getting big, there's a higher degree in the denominator, so this is going to tend towards 0. All right. One more here. Y equals 6x squared over 2x squared plus x minus 15. If I want to figure out the domain, I need to factor that denominator and find its zeros. So if I want to factor this, I need factors of negative 30 that add up to 1. Those are plus 6 and minus 5. I can factor this, 2x times x plus 3 minus 5 times x plus 3. So I can see my factors are 2x minus 5 and x plus 3. Okay? And I want to know, what are my vertical asymptotes? Well, if I set these each to 0, what would I get? if 2x minus 5 equals 0, I add 5, divide by 2, get 5 halves. If x plus 3 equals 0, then x is equal to negative 3. And I see I have 2 vertical asymptotes once again. How about my horizontal asymptote? Well, again, compare the leading terms. 6x squared over 2x squared is 3. So my horizontal asymptote is y equals 3. Be careful here. When I'm writing my domain in interval notation, I have to skip both of these two values in my vertical asymptote. Remember, please, domain and vertical asymptote are interrelated. So, I go from negative infinity up to, but not quite reaching negative 3. I have a second interval from negative 3 to 5 halves. And then I can go from 5 halves to infinity. These are a little bit hard, unless you really get into graphing these and picturing them. This is a little bit strange, but again, it's that whole idea of the domain is everything but the restricted values, the things coming from the vertical asymptote. That's most of the content you need to know. I'm going to do one last example here. We're going to take one of these general looking equations and graph it. So here, I have f of x equals 2x minus 4 over x minus 3. Step 1 is to figure out my asymptotes. So I can say x minus 3 equals 0, which means my vertical asymptote is x equals 3. For my horizontal asymptote, I'm going to compare 2x and x and get 2, which means my horizontal asymptote is y equals 2. And then again, I know what's going to happen is this is going to be somewhere in those regions, in those arcs. Okay, and again, you may use a calculator if you need to, but when we're getting more points right here, I want to think about what happens when x is, say, so this is 3. How about if x is 2? I will have 2 times 2 minus 4 over 2 minus 3, which is 4 minus 4 over negative 1, which is 0. What about if x is 1? There I'll have 2 times 1 minus 4 over 1 minus 3, which is 2 minus 4 over negative 2, or 2 over negative 2. Excuse me, negative 2 over negative 2, which is positive 1. So that gives me a general idea. What this curve is going to look like is something like this. It's going to curve through those 2 points and then get really close to the asymptote without ever quite hitting it, because that's what an asymptote is. I could draw this better. It should get closer. All right, how about the other side? If I put in 4 for x, I will have 2 times 4 minus 4 over 4 minus 3. So that's 8 minus 4 over 1. So up here I'm going to be at 1, 2, 3, 4. Like I said, the pattern of how these points are laid out is not super friendly or interesting. You can always just plug in numbers, though. So if I put in 5, I'll have 2 times 5 minus 4 over 5 minus 3, so that's 10 minus 4, which is 6, over 2, which is 3. So I see this thing right here. And again, I will connect it and draw it getting close to the asymptotes. Okay. So that's just a quick look at this. Again, be aware, these can look differently. None of the examples I did included a reflection. If I did have something with a reflection, would see something a bit different. I might have something like y equals negative 3 over x plus 1 plus 2 or something like that. In which case I can see I have a vertical asymptote of x equals negative 1, a horizontal asymptote of y equals 2, and if I found points, what the reflection, what that negative is going to do is actually put these curves up here and down here. And it's just a very general sketch of what that might look like. Hope that makes sense. Good luck.